So it is now my pleasure to introduce the second talk of this session and our speaker, Anima Anandkumar. Anima is a Bren Professor at Caltech, and she's also Director of Machine Learning Research at NVIDIA. She was previously a Principal Scientist at Amazon Web Services. Her research focus is on unsupervised AI, optimization, tensor methods. She has received a number of awards, including the Sloan Fellowship, Young Investor Awards from DoD, and faculty fellowships from Microsoft, Google, Facebook, and Adobe. And Anima is also part of the World Economic Forum's expert network. So please join me in welcoming Anima so that we can hear about her talk on AI for Science, Convergence between AI and Scientific Computing. There's your clicker.
Thank you, everyone, and thank you, Vivek, for inviting me here. And just so great to be back in person and catch up with everyone here. So today I'll talk about the exciting convergence we are seeing between AI and scientific computing. And this is something both at NVIDIA and Caltech, there's a lot of interdisciplinary efforts to bring together AI algorithms, but make them really relevant for scientific applications and handle the hard challenges there. So let me start with some of the results we've seen as part of this AI for Science. To begin with, I think the exciting result is the ability for AI methods to now solve partial differential equations, and sometimes with very good speedups, more than 1,000 times faster than traditional numerical methods. One of the recent advances that we announced at GTC last week, Jensen Huang announced in his keynote, was this latest weather model where we are able to speed up by 100,000 times compared to traditional numerical methods, but also be of a much higher resolution compared to the previous machine learning methods. And so here you see that these purple contours are what's predicted by our method. And this is the Hurricane Matthew, and you see a very good ability to predict these extreme events, even though there weren't many of them in the training set, and be much better than the white contour, which is the traditional method. So not only is it faster, it can also be more accurate many times compared to the traditional methods. We also see that in other applications. Another one we worked on is carbon dioxide sequestration. The ability to capture carbon dioxide and store, whether in subsurface or deep under the earth, requires multi-phase flow modeling. So how carbon dioxide interacts with water and the pressure buildup that can happen, which is very important for safety considerations. And again, in this case, we were able to model this and get 60,000 times speed up and accurately predict these pressure buildup and gas saturation. We've also developed machine learning methods for drug discovery. In fact, what we are able to do is accurately capture both domain-specific features like orbital information and combine it with graph neural networks. So you're having both the domain knowledge as well as the flexibility that machine learning methods can do. As a result of this, our method called ORBNET is able to do, let's say, for instance, geometry optimization in chemistry applications more than 200 times faster than current methods, current numerical approximation methods, and also be more accurate. And in fact, one of the Gordon Bell finalists for the special prize that will be announced today is also incorporating this method where for the first time we have a billion atom simulation of how the delta variant interacts in the aerosol. And one aspect there has been to have more accurate quantum mechanical calculations using this ORBNET method. It's replacing the traditional DFT method and is more than 1,000 times faster, but also able to achieve a scale that wasn't possible before of thousands of atoms and coming up with these energy calculations much more accurately. I'll now give you a few other aspects of AI algorithms that we've seen advances in and how they're relevant to scientific applications before diving into how we made these achievements possible, what are the ingredients in designing the algorithms. And so one important aspect is trustworthy AI. Thankfully, there's a lot of awareness now on the need to not just have the best accuracy, but also the best fairness, right? Best uncertainty estimation. And even for scientific applications, this is really important because we want to think about generalization in an out of distribution manner. And so that's where, for instance, in this drone landing application we did at Caltech, what we require, I'm not sure why that happened, is the ability to land safely and at the same time be efficient, right? If you see a lot of commercial drones landing very slowly can result in a lot of wasted battery. So the need for good uncertainty estimation of how safely can you land while being fast is important, and also safely explore and keep landing faster. And we are able to develop methods that can work in high dimensions with deep neural networks, but also get good uncertainty calibration even under distributional shifts. The other important aspect is differential privacy and federated learning when it comes especially to healthcare data. And when in an unprecedented manner, we were able to get 20 hospitals to train within 20 days a model for assessing both the X-rays as well as other healthcare data to come up with a prediction of outcomes in a federated learning manner. So in a lot of applications, I think scaling up differential privacy or coming up with guarantees on what kind of attacks can happen is important, and this is another area that's relevant, especially in healthcare. The other important aspect is simulations. I told you in the beginning that we're able to use AI to replace traditional methods for scientific simulations. The other side of the coin is using simulations to train AI. Right? So in many cases, you cannot get a lot of good quality real-world data, especially in robotics. And so at NVIDIA, we are building physically valid GPU-accelerated simulators for a number of settings. And so the one that I'm showing here is the legged robot. And by training it extensively in simulation, for all kinds of different tasks, right? And also doing it as a hierarchical reinforcement learning, we are able to transfer it to the real world. And the agent is able to learn in a robust way the ability to handle different situations. And we've also seen that in a number of other settings. For instance, in another application with robotic arm manipulation, can it quickly adapt to new tasks, right? And can it have model-based, say, domain knowledge and representation, but also have the adaptivity? I think the dual sides of it is important for these robotic applications. And so what we did was to build on top of the traditional operational space controller methods, but make it learnable in terms of the parameters there. And so with that, you see that it's also able to quickly adapt to a new task specification. And so what this shows is simulations are also central to developing machine learning methods, especially in the context of applications like robot learning, where real-world data is hard to get. And in computer vision, there's a lot of exciting developments we are seeing, especially with reducing supervision or going completely to even self-supervision, right? So if you can generate your own supervision with the availability of invariances in your domain, right? So for instance, simple data augmentations like cropping or adding noise can make it much more robust in learning, and as well as the ability to easily fine-tune into downstream tasks. So in this example here, what we're able to show is if you only give box supervision, the bounding boxes as labels during training, you're directly able to learn also instance segmentation and correspondences. So you're able to easily go with simple weak supervision to more complex tasks. And the other important aspect is zero-shot robustness, right? So I'll emphasize about zero-shot generalization in this talk because in a number of applications, you cannot always incorporate everything in training data. So designing state-of-the-art transformer models that are not only very accurate, but also have this robustness and other zero-shot generalization properties is something that we are looking into. And so, I showed you a range of developments, right? So what are some underlying themes here? So the way we think about designing an algorithm for an AI system, right, I can break it down into 3 parts. We have to think about what kind of data is available. I showed you instances where we are combining simulations with real-world data. I showed you instances of weak supervision and self-supervision, right? So, and then in terms of the priors, what additional knowledge and constraints from the domain can I incorporate? I showed you the example of ORBNET, where we can use the orbital information with graph neural networks, and as well as the equivariant properties of rotational symmetries. And then the task specification, do I just train it for one task or a variety of tasks? You saw the example in where the legged robot being trained on a variety of different tasks makes it a lot more adaptive and robust. And so I think these aspects we all need to think about when designing it, and especially in scientific applications, it's very important to incorporate all these facets. Right, so ultimately, the way we want to go is to, hopefully get all the way to unsupervised learning. We're not there yet, but at least reduce the supervision whenever possible. It's very important for scientific simulations because, yes, there are ground truth simulations available if you have very expensive methods, but you cannot afford to generate a lot of those. And in examples like the Gordon Bell finalist, the special prize finalist, where I showed the scale, right, of the quantum mechanical calculations over thousands of atoms, it's not even feasible to get the ground truth data at that scale. So you can only hope to train on smaller scale or small molecules and directly generalize to large molecules. And so this kind of zero-shot generalization can only happen if you incorporate additional domain knowledge and constraints, right? And then also the last aspect of the task specification, especially if you're thinking about interactive learning and robotics, adaptivity is an important aspect to think about. So that's an overview that I wanted to give, in terms of how to go about designing algorithms involving AI in a number of different applications. The other aspect is the co-design of hardware and software. In this talk, I won't go a lot more into it other than to give you some overview here, but we did go into it much more in depth on the panel that I was part of on Tuesday. So if you're interested, I encourage you to go and also check out the presentation from there. So, one aspect is this co-design, right? So far, we're thinking of hardware as a substrate, and we design the algorithm independent of that. But are there scenarios where we can make hardware efficiency be even better if we can co-design it with the algorithms that AI systems involve? And so one aspect we went about asking is, can we look into harsh quantization? Quantization with just 8 bits, but still retain the accuracy of full precision training. So this is not just quantization at inference time. So we are quantizing and training it directly in the quantized system. There is never a full precision copy, right? So even with that, we have no loss in accuracy. If you directly did it as int 8, right, integer 8, this wouldn't be possible. The performance would drastically go down. But instead, by doing it as a logarithmic quantization, we are able to maintain accuracy. And for this, you cannot just run a standard stochastic gradient descent method. What we realized is having the ability to do it as a multiplicative update was very important to get this model to train well. So this kind of co-design of hardware and AI algorithms is the future, right? And we are only beginning to scratch the surface. And with this, we were able to get as much as 90% reduction in energy. And the other aspect is also, having efficient hardware, efficient GPU implementation for other next generation hardware, such as quantum computing. And in this here, we did a world record run in terms of more than 3,000 vertex max cut problem, and being able to solve that with high accuracy. And this again involved a new quantum optimization algorithm involving multi-basis encoding and designing efficient frameworks like TensorLink Quantum, which we've also open sourced now. So it's like a lot of components have to come together in order to, of course, right, scale up these systems, and efficient algorithms can help us take us much further than otherwise. So that's an overview that I provided on some of the exciting developments. Now I'll go a bit more in depth in terms of what these methods involve, right? So what are the core foundations that enable us to obtain these results? So the first aspect I want to cover is, if you want to learn PDE solvers, right, instead of using the numerical methods, if I want a machine learning method instead, we have to think about learning in infinite dimensions. So I'll come to what I mean in a second, but the first aspect is, right, there is a difference between just solving an instance of a partial differential equation to learning a solver over multiple instances. And so for the first one, all you need to do is output what is the solution at each query point. But if you now want to learn solving many different instances, right, you need generalization. So you need, training instances, either training instances with the ground truth solution or training instances where you're just given the equations, right? So, but you need multiple instances to learn about the family of partial differential equations. And this is where it's different from standard deep learning, because they're mostly designed for fixed resolution inputs. So they expect inputs of a fixed discretization. On the other hand, we know, if you're solving partial differential equations, we need the flexibility of using different discretizations or different, grids. But also we know that the underlying solution is continuous, right? So if you are overfitting to one resolution, that's likely a bad, like solution. It may not generalize well to other instances. So by changing the paradigm as learning mapping between function spaces in infinite dimensions, we are now able to get much better generalization. And the other benefit is training just even in, say, low resolution and directly generalizing to high resolution evaluations is a benefit we'll see by using such a paradigm. And so this is what we call the neural operator. So how do we now go about designing architectures that satisfy this resolution-free property? And so to do this, we start with just thinking about what a standard neural network has, right? So it typically has multiple layers. Each layer is some linear operation, like say matrix multiplication or convolution. You have nonlinearity, you compose that together. So that's how we've designed all our neural networks so far. So can we now extend it from finite dimensions to taking inputs and outputs that are potentially infinite dimensions? So to do that, what we need to do is to replace these linear functions in the layers with linear operators, right? So that was the idea that we now for neural operators, we need to design linear operators, combine them with different nonlinearities. And so overall, we can get a universal approximator for any operator. So the question is, what would be an appropriate linear operator? And this is where we can take the intuition from looking at the solutions for linear partial differential equations. So we know that it's the Green's functions, right? And you're doing an integral operator over it. Or in other words, we're doing a global convolution with the kernel given by the Green's function. And so if we formulate it this way, we know this is now not fixed to a given discretization, right? This is directly learning the operator. And indeed, a simple example of such an integral operator is the diffusion equation, right? So in this case, we analytically know what the Green's function is. But in most cases, you don't. And in fact, to solve nonlinear PDEs, we are doing several layers of such linear operators. So this is something we have to learn from data rather than an analytical form. So how do we now design an architecture that can solve such integral operators? This is where we'll use the familiar trick with the Fourier transform, or even like other bases, right? So the Fourier is a natural basis for many families of partial differential equations. In fact, even the numerical solvers use this in instances like Navier-Stokes. So what you can do is you can solve the integral operator in terms of in the Fourier domain, it becomes just multiplication. So we are learning the weights in the Fourier domain. And the other benefit of doing Fourier transform is that it can incorporate global long-range correlations, right? Whereas if you're learning a convolutional neural networks, the filters are usually small, so you're only learning mostly local behavior, right? The receptive field is small. And so that's the other benefit we get by using this. And so what we did was to now, the integral operator, we solve it through the Fourier transform. We're learning the weights in the Fourier domain. And then we're only filtering and keeping the low frequency modes before doing the inverse Fourier transform. Of course, if you just did one layer of it, this would be very limiting for multi-scale phenomena with high frequency. But on the other hand, we are doing nonlinear transformations, so over a few layers, you can still capture the whole spectrum. And this is a nice regularization we saw by using only the low frequency modes in each layer. And so what we see with this is the ability to just train on low resolution data and directly evaluate it at high resolution with good fidelity. and be 1,000 times faster than pseudospectral solvers that are also on GPU. So these are as efficient as possible, and we still can be 1,000 times faster than that. And you also see that in the way the spectrum is captured, the unseen part means it's a zero-shot generalization, right? So at training time, there was only low-resolution data available, so it couldn't have seen this higher frequency spectrum, but it's still able to generalize. And that's because of the paradigm of learning the operator, so it's able to capture that phenomena still fairly well. And what I showed you earlier, the weather forecasting, we are doing that on the ERA5 dataset. We'll soon release a paper on this where we are able to get accurate predictions even of extreme weather events while being 100,000 times faster, as well as multi-phase flow problems that we see with the carbon dioxide sequestration application. This is another Gordon Bell finalist for the special prize today, where we used this formulation, but with the graph models, right, for the molecules, so graph neural operator, and showed the ability to model the time-dependent conformal changes that happen during the replication process. So I also encourage you to check out that paper and the talk in detail that has a number of exciting aspects of doing molecular dynamics at an unprecedented scale. And one aspect is how these kind of machine learning methods can further speed up our molecular dynamics simulation. And many other applications. I won't get into them in detail here. We have papers that are already out or upcoming in terms of the ability to not only speed up calculations, but many times also be more accurate, especially if this is real world data and there are modeling errors that are present in standard methods. Yeah, so also wanted to quickly point out there is a nice connection with transformers, because the self-attention layer, you can think of it as if you look at, have a continuous generalization of it, that becomes a neural operator. So we are also seeing promising benefits of speeding up self-attention layers using these mechanisms. And we are building all of these methods into NVIDIA modulars for AI accelerated physics simulation. So stay tuned for the ability to have open source scalable methods and models that work with the pipelines at the industry scale. So I want to now spend a bit more time on the other applications I talked about. One is in quantum chemistry. So how do we replace traditional DFT calculations that are very slow with AI-based approaches? And what we did was to combine molecular orbitals with graph neural networks. So if you directly just used a graph neural network on a molecule, the problem is it can only capture low, short-range correlations, right? And that's not going to generalize well if you only train on small molecules and directly generalize to large molecules. But on the other hand, the orbital features give it that invariance. And so this is how we can get zero-shot generalization and apply it to much larger scenarios than the training data. And the other aspect we incorporated was 3D symmetry, like making these networks equivariant to orbital inputs, orbital features, and that also enhances the generalization ability. Yeah, so with this, what we see is, the method Unite is a version of the ORBNET that I showed you with equivariance. I get DFT level accuracy, but be 1,000 times faster. And also in terms of data efficiency, it's much more data efficient than any of the other deep learning based methods because we use this orbital information, right? So this is where the right kind of domain priors can really enhance the ability of machine learning to generalize well and work with less data. And so I showed you this geometry optimization earlier, and also the ability to capture the quantum mechanical calculations of the calcium cations in the system there, and do that at a scale of thousands of atoms, which is unprecedented. Yeah, so in the last part, I want to spend some time looking into how we are able to also simulate the next generation hardware such as quantum computing and make that efficient on GPUs, right? So there are multiple benefits for this, right? So one is, of course, as we push the realm of what you can simulate on classical computing, that creates a benchmark for what you can hope in terms of quantum advantage. The other is in terms of course, a lot of aspects of algorithm design, architecture design, right? It would be too clunky to do it directly on quantum hardware. You need effective simulators to look at the efficacy of different algorithms. And so that was our thinking to release Q-Quantum. We announced it at GTC last week. And there are many different partners, including Google, who have been using this with good success. So one of the methods that I want to show we did with Q-Quantum is in the space of this variational quantum computing. And the idea is, with this, the setting of variational quantum computing, we are looking at moderate entanglements rather than the much harder to realize high entanglements. So many experts believe this is much nearer term than the quantum supremacy regime. And so here we use tensor networks. This is near to my heart, right? So I've been working on tensors almost a decade now, which is hard to believe. And what we see is, the ability to go to higher dimensions can be useful in so many applications. I started with working on probabilistic models, learning latent variable models using method of moments using tensor factorizations. And we can similarly do that in other settings. And so in this setting of looking at quantum circuits, we used tensor trains or matrix product states, which is a very simple form of tensor networks. It only has nearest neighbors connections. So it's fairly low entanglement compared to a fully connected tensor network. So the question is, even these fairly small amount of entanglement, is it effective in solving hard classical optimization problems like max cut? That's what we wanted to investigate. And the other aspect was, can we more efficiently encode these classical optimization problems into quantum circuits, right? Because the simple thing what people do is take each vertex in the graph for the max cut and encode it as a qubit. But instead, what we went about, I'll come back to this in a second, is to do a multi-basis encoding. And what we did was the ability to use both the x and z axis spins or the quantum spins to encode the vertices. And so with this, what we have is a nonlinear quantum optimization algorithm. But the benefit is we are requiring only half the number of qubits, right, compared to the standard method. And so you're getting this exponential reduction in simulation complexity because simulating half the number of qubits on GPUs is exponentially faster. And so with this, we are able to now scale up to unprecedented sizes of graphs. In this case, more than 3,000 vertex graph has about 97% accuracy, right, in recovering the maximum cut. And in fact, even going all the way up to 10,000 vertex graph, we're able to get at 93% max cut, but when we stay at the same depth circuit, which also shows as you scale up the number of nodes, it does become more challenging. And at the same depth, you cannot expect, right, the accuracy to be the same. You need a much, much higher depth. So it's also kind of giving us a notion of scaling of how these quantum circuits would work in terms of solving these problems. And that's where I think these kind of simulations are very beneficial. And so we did this on the Selene DGX SuperPod at NVIDIA, and we were able to accomplish by building this with the Q-quantum right, acceleration. And on top of it, the TensorLeak Quantum is the open source framework that made it possible. So that's the TensorLeak open source framework. It's an ecosystem with hundreds of thousands of downloads that are already there. So that's a mature open source framework. And on top of it, we built TensorLeak Quantum to enable these quantum algorithms also very efficiently. So I encourage you to go check it out. Right, it can connect to the original TensorLeak, can connect to many different backends, while the TensorLeak Quantum is built on PyTorch. So you can easily just describe any tensor operations as layers in PyTorch and just use it, as part of all other deep learning algorithms or other algorithms you want to work with. And so that's what makes it so easy to use out of the box. Yeah, so to conclude, in fact, that was my last slide. I strongly believe that AI for science is the future of science, and we are just beginning to scratch the surface in the potential it holds to replace or augment current numerical methods with AI and get many orders of magnitude speed up. But we also need to go about this thoughtfully, right? Like look at what are the domain-specific constraints and requirements. So for solving multi-scale phenomena on continuous domains like partial differential equations, we need to be able to have a resolution-free manner that learns directly the underlying operator, which is the mapping between infinite dimensional spaces. And I showed how neural operator and FOURIER neural operator can do this efficiently. The other aspect is when modeling like quantum chemical properties in molecules, we need to worry about the domain constraints like symmetry and domain-specific features like orbitals. That makes it a lot more effective to do zero-shot generalization and going to much larger molecules than what we've seen during training. And lastly, I showed how tensor methods can be very effective in simulating quantum circuits, and by designing efficient nonlinear quantum optimization algorithms, we can be much more effective in encoding our problems into quantum circuits. Thank you.
Thank you for a really interesting talk. It's generated a number of interesting questions. So we have time for a couple. I'll batch together one set of questions that relate to validation and fidelity.
Yeah.
So how do you validate these AI-based approaches? What is the false positive, false negative rates? How would you approach it if you don't have a baseline already for a PDE solution?
Right. So indeed, in terms of like baselines, right, we can look at standard neural networks like UNets and see their ability to work here. And there, we do see if you try to do it to a high resolution using simple interpolation methods, it doesn't work, right? Because we know multiscale phenomena are not captured if you just overfit to one resolution. The other is, in terms of validation, the good thing about partial differential equations is it's very easy to verify whether we have the right solution or not. So we have now a new paper that we just released called Physics-Informed Neural Operator, where we can further fine-tune on an instance given the equations, right? So we can make sure further that it will solve the equations to the required level of fidelity, same as you would do with a standard solver, right? You can decide what is the level of fidelity that's needed, and so this way we don't have to rely just on the generalization ability. We can further fine-tune it to a given set of equations.
Good, thanks. And another set of questions relate to performance. The 1000x improvement is really impressive. How do we weigh in the amortized overhead of the training? And could you just give some idea of how the times to spend training and how much whether retraining would be needed and so on?
Yeah, I mean, it really depends on the application. In the Navier-Stokes example I showed, we required less than 1,000 samples, which is not a lot compared to the millions or billions you see in other AI methods and other tasks, right? But also, the aspect is here the diversity is much lower than, say, natural images or natural language, right? So it need not be at that huge scale that we require. And the other way to think about is, training, I think, it really depends on how often, and how much you would use this method, right? Because a lot of programming and other time goes into even the traditional methods and incorporating other domain-specific features there. So I would say it's dependent, but as a whole, this method is quite efficient.
Okay, that's great. Let's thank Anima again. Thank you.
Thank you. Thank you.
Thanks a lot. That was a great talk. And that concludes this session. As a reminder, we have another invited talk session at 10:30 where there'll be talks by Larry Smarr and Kim Hazelwood. Thank you all.